So far when we've been looking at electric circuits, we've been looking at circuits where the current flows only in one direction. And that is not how things work when you plug into a wall outlet. So now we'll go ahead and turn our attention to AC circuits. And we'll start just by defining the terms DC and AC. So DC stands for direct current. And this means the current flows in one direction only. So your typical battery circuit that you wire up, this is the sort of thing you'll see. AC stands for alternating current. Alternating current. And this means that the current flows back and forth in an oscillatory manner. Oscillatory manner. Now, within the physics community, it's become fashionable to extend the ideas of DC and AC to mean something that's constant in the case of DC, or something that has some sort of sinusoidal behavior, some sort of oscillatory behavior in the case of AC, regardless of whether it actually has anything to do with electric circuits or not. So you may run across that usage, but here I'm going to be restricting it to talking about electric circuits. Now, why would we want to do AC? It seems more complicated. And turns out there are a few good practical reasons. So the reason that AC gets used in commercial transmission of power is two main reasons. One, it's much easier to run an AC motor than a DC motor. And the other reason, which is the bigger reason actually, well, commercial customers really like this one, but from the power company's perspective, it also allows for the use of transformers. These are uniquely AC devices that will run across in the next video. But what this will do is that this device allows the utilities to minimizes heat losses in the transmission lines. Basically, what these transformers will do is they'll allow the utility to increase the voltage and decrease the current simultaneously. And since resistive losses go as I squared R, as the square of the current, if you can cut the current in half, you cut your resistive losses in a quarter. Now, when we've been looking at practical DC circuits, we haven't been too worried about the losses that you have in the wires that hook things up. But the difference when you're an electric utility is you have many, 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 many kilometers of wire. And even though the resistance of the wire isn't all that high, the resistivity isn't all that high, you just have so much length that it actually becomes a pretty significant factor. So much so that if you remember your history about the Battle of the Currents, one of the big problems with doing DC transmission is because that was at lower voltage and higher current. So it would have been necessary to actually create an electric utility generator about every 2 blocks. These generators wouldn't be very efficient. Generally speaking, the bigger you can make an electrical generator, the more efficient it is. So these wouldn't have been, these power plants wouldn't have been very efficient, and just the voltage losses for even short runs at comparatively lower voltages just were not tenable. Now, this all being said, as we get into this, we'll see that we haven't completely buried DC yet. In fact, in some ways, it's making a bit of a comeback. This is because solar panels, which are becoming a bigger and bigger means of producing electricity, are uniquely DC devices. And there's more and more use of stationary storage batteries, which batteries themselves are DC devices. So there's a bit of a balancing act between the AC and the DC side. And we'll see that there's even for very, very, very long runs of transmission line, some new technologies are making DC a viable choice in that case. But that's coming up in later videos. All right. So with that, let's go ahead and just start by describing the EMF of an AC source. So this could be just literally plugging into your wall. The voltage across the prongs in the outlet. Let's try that again. EMF of an AC source. If you measure the voltage, measure the voltage as a function of time across the prongs of, say, a household outlet, you'll see that it. Let's try that again. All right. You'll see that it varies sinusoidally with time, or in this case, I drew it as a cosine. So it'll go between plus some maximum value of the EMF. We'll write that as EMF sub 0 here. This would, and minus that same maximum value. So this is our amplitude. This is a simple harmonic oscillator, so the time from peak to peak will be the period. And we remember that the frequency of oscillation is 1 over the period. So we can write the EMF as a function of time as the maximum EMF times the cosine of 2 pi ft. Now, technically, I should be writing the EMF symbol left parenthesis t, right parenthesis. But in the world of AC circuits, this is quietly understood to be read as the EMF as a function of time. And we just don't bother writing the of t part. So when you look at this, you should think that. And that's pretty standard notation. Now, as far as typical values for these frequencies, if it's for power transmission, pretty much there are only 2 values that it could be. And while there are exceptions both ways, roughly, if you're in the New World, so for the most part the Western Hemisphere, the frequency that power is transmitted at is 60 hertz. There are exceptions. There are countries in the New World where 50 hertz is used. And if you're in the Old World, so Europe, especially other parts of the Eastern Hemisphere, the transmission frequency is 50 hertz. And again, there are exceptions there. And where some countries in the Eastern Hemisphere will use 60 hertz. But just very roughly, that's how it divides up. And why these values? It turns out that for practical electrical engineering reasons, you need a frequency somewhere around here. And in the New World, as people were developing this stuff, they just went with the idea of, hey, there's 60 minutes an hour, there's 60 seconds in a minute, so we'll just oscillate our frequency 60 times a second just to keep the 60s going. In the Old World, they said, well, 50 is half of 100, so that was basically the choice they made. It was just a nice computationally convenient number. There's nothing really to pick between one or the other. It would have been nice if there had been more communication across the planet when this stuff was being set up, so we could have just picked one value, and for that matter, come up with one way of transmitting power. But that's what we've got. Basically, the only thing where it'll matter, say if you're traveling internationally, as far as the frequency goes, is if you have a motor. It turns out that motors in the New World will have some RPM that is a multiple of 60 hertz. And in the Old World, it'll be some multiple of 50 hertz. And so if you run a motor in the other part of the world, it won't be running at the optimal design RPM, and you can wind up stressing the motor. But for pretty much anything else, most computers, things like this, they have automatic switching power supplies at this point, so usually all you need is just an adapter that changes the shape of the plug from where your computer was meant to be used to where it's going to be used, and the power supply in the computer will just automatically measure the voltage, measure the frequency, and then configure itself to work with that, since it's just providing DC to run the computer anyway. All right. Now, within a device, say a radio or things like this, where you are having current, where you're making current oscillate for a reason within some electrical device, then your frequencies will typically run anywhere from about 100 hertz up to about the gigahertz region, so 10 to the 9 hertz, just as a very rough benchmark. Okay. So let's go ahead and just take a look at a circuit that is just a resistor hooked up across an AC source. So the symbol for an AC source is a circle with a little squiggle in it. This squiggle is meant to look like a sine wave. And then we'll just go ahead and put a resistive load across this. This is literally your toaster or a space heater or something like that. So the voltage of the source will be equal to the EMF. This will be the resistance. And then the current will slide as the voltage changes. We'll have a current that's sloshing back and forth. Now, usually the way we'll write this is we'll say the voltage across the resistor. We'll use a lowercase v and sub r. will be equal to whatever the maximum value is times the cosine of 2 pi ft. And the current as a function of time, use a lowercase I for that, through the resistor will be the maximum current times cosine 2 pi ft. And again, here, these lowercase letters are telling us to think of the that this is just a way to suppress writing of t. This is really the voltage across the resistor as a function of time. This is the current through the resistor as a function of time. And again, this notation is super standard. So when you see lowercase v, lowercase I, this is the voltage as a function of time. This is the current as a function of time. All right, so we can go ahead and use Kirchhoff's loop law here and say that the EMF as a function of time, so we go through, we change by the EMF minus the current as a function of time times R equals 0. And we get, or we could say that that's the voltage across the resistor. Either way. All right, so what this means is that our current, since this is going as a cosine, will have both plus and minus signs. This means that our charges just keep sloshing back and forth through the resistor. They never really move very far at all. Remember, typical drift velocities are on the order of a millimeter a second, if that, and the current is oscillating 50 or 60 times a second, depending where you are in the world. So just the charges are just barely sloshing back and forth in place, but it doesn't matter. They still keep colliding with the atoms that make up the wire and make up the resistive wire in the toaster. And your toaster heats up and it makes toast. All right, well, let's go ahead and plot. So taking a look at this, what we can see here is that if I were to plot both the voltage across the resistor and the current through the resistor on the same graph, 2, 3, 4, we'll make this one period like so. So I'll plot the voltage across the resistor in green. So this will run between some positive maximum value and some negative maximum value, VR. And it'll look, if it's a cosine, it'll look like that. And similarly, we can see that whatever the EMF source is doing, that's what the current has to be doing at the same time. So I can plot the current, and I'll plot that just on the same graph. I'll do it in purple. So they'll be between some positive and negative maximum value. And there's absolutely nothing to be read into the fact that I made the current smaller on the graph, because the voltage is in volts, the current is in amps. They have different units. There's no way to meaningfully compare them on the same graph. All we can just say is if they're going, how one is going up and down versus how another one is going up and down. And what we get here is that whenever the voltage across the resistor is high, the current through the resistor is high. And whenever it's low, the current, whenever it's negative, the current's flowing the other way. When the voltage is 0, there's no current. So the way we say this is that since they're always acting in sync, we will say that the instantaneous voltage and the instantaneous current are in phase, which is physics speak for doing the same thing at the same time. We will see that for other devices, this won't be true, but it is true for a resistor. Okay, so with that, let's go ahead and talk about characterizing power and also how we talk about voltages and currents. We'll use what are called RMS values. So if I plot the current as a function of time, let's say, through our resistive load or whatever, like we just said, we'll go from between plus and minus some maximum value. And this time I'm going to try to draw two periods. One period, two periods like that. All right, so if you were to look at this, you might say, what is the average value of the current? So if I just let it oscillate a whole bunch of times, on average, what's the current? Yeah, 0. Half the time the current's going one way, half the time it's going the other way. We have matching everywhere you look. You got some region where it's positive, some region where it's negative. The average value is 0. Now, that being said, I wouldn't exactly run around and say, oh, that means I can safely stick my hand inside a toaster while it's operating. Even if it's technically correct to say the average value of the current is 0, there is definitely a current flowing through it. So we resolve that the same way we resolved the issue about back in thermodynamics when we talked about the average velocity of molecules. We said that the average velocity of air molecules in a room was 0, but that wasn't too useful. And so what we used instead was, on average, how far away are you from 0? And in the case of air molecules, we got that by squaring all the velocities, taking the mean or average of that, and then taking the square root of that average. So that's what RMS stands for, root, mean, square. You square everything, average the squares, take the square root. In some sense, that gives you an idea of, on average, how far away are you from 0? This turns out that you can do exactly the same kind of thing here. To thoroughly argue it, you'd have to use the methods of calculus, but what we can do is say, well, for my toaster, what is if I were to plot the power being radiated off, I know that the power goes as I squared R. So this is going to look like, if this is a cosine here, what the power as a function of time is going to look like is cosine squared. Try to do that a little better. There we go. There. This will go as cosine squared, so proportional to cosine squared of 2 pi ft. And we can characterize in the average power. So if you were to if you use a super high-speed camera, you'll see that the glow in your toaster pulses 100, in North America pulses 120 times a second. The current sloshes back and forth every 60th of a second, but whether the current's going one way through the toaster or the other way through the toaster, it'll heat up the element. So for every 60th of a second, there are 2 pulses of heat being radiated out by the toaster. Now, when you're making toast, you don't really care that you're getting 120 pulses of heat a second, or 100 if you're in Europe. What you care about is just the average. And you can argue that the average power radiated is 1/2 of the max current. So this is our maximum current squared R. And I'm just arguing by saying, hey, if you plot out cosine squared and you draw it better than I do, this piece here will fit perfectly into that piece there. And so the total energy and the area under the curve here would correspond to the energy being delivered. So the total energy being delivered by this thing is the energy delivered by that you get by saying it was a constant value that at 1/2 of the max. So the way that this works out is it ties in nicely with the RMS values. You have to use the methods of calculus to obtain them. But what we can do is we can define the RMS values of, say, current and voltage to be, so if we just write I without saying anything, that will mean the RMS value. And that will be the maximum value divided by the square root of 2. And same thing for voltage. If I just write a V without a subscript, that will mean the RMS value. And that will be the maximum voltage divided by the square root of 2. So if I work in RMS values, if I do, say, I squared R here, if I square this, I'll square this, and I'll square that square root of 2, which will give me that 1/2. So I can, if I use RMS values, I can get back the typical sort of expressions that you see in DC, although there will be, at some point we'll have to introduce a thing called the power factor for some more complicated circuits. But almost everything that you know how to write in DC, you can write in AC if you use the RMS values. So when voltages or currents are specified and it's not said otherwise, then that means the RMS value. So let's go ahead and try making that concrete. Let's say you have a nice vintage 60-watt incandescent light bulb lying around. Of course, you can't go to the big box store and buy them anymore now that we've made the switch to LEDs and CFLs. And when you say it's a 60-watt bulb, you have to say where in the world it's meant to operate at 60 volts, at 60 watts. So we'll say North America. So that means that it's meant to be plugged into an 120 volt outlet. Now let's go ahead and figure out the RMS current, the resistance of our bulb, and then we'll also figure out the maximum current and the maximum voltage, just to get some sense of how this all works. So just like before, we can say the power is equal to IV for a purely resistive load. And so the current will be the rated power over the voltage that was meant to operate in. So the rated power is 60 watts. If it's meant to operate in North America, that's 120 volts. That's going to give you 1/2 of an amp. From that, we can go ahead and figure out the resistance. There are many ways we could do it, but I'll just go ahead and say twinkle, twinkle, little star, V equals I times R. So R is V over I. So this will be 120 volts over our 1/2 amp current. Means that that old incandescent light bulb had a 240 ohm resistance. Now remember, this current here is the RMS current. So now let's go ahead and figure out what the maximum value of our current is. And that'll just be multiplied by the square root of 2. So our maximum current will be square root of 2 times the RMS value. So it'll be the square root of 2 times 1/2 an amp. So this will be 0.707 amps. And similarly, the maximum voltage, the amplitude of our voltage, will be the square root of 2 times the RMS value of our voltage, which is the square root 2 times 120 volts, is 170 volts. So when you say that you have a 120 volt outlet, what that means is the voltage across the prongs in the outlet is actually oscillating back and forth between plus and minus 170 volts. So again, you can say that the average voltage is 0, and you definitely don't want to put your tongue across the outlet thinking that you won't get shocked, right? So you're more interested in, on average, how far away are you from 0? And it turns out that that's 120 volts. But to do that, you could swing out as far as plus and minus 170 volts while it's oscillating. Alrighty, so in the next video, we'll go ahead and introduce AC circuits and, introduce transformers and talk about some of the practical details of power transmission. Catch you over there.